Alright guys, these are solubility notes. We're going to look at the solubility curve graphs that we kind of touched on last week and get into some specifics and look at how to read them. Some words that you need to know right off the bat, I'm going to go ahead and write these out to the side, are unsaturated, saturated, and supersaturated. Okay, what this basically means is the amount of solute. Remember, the solute is the stuff that goes into the solvent. Solute goes into solvent. So I'm going to give you an example if I'm making lemonade. So your lemon and your sugar. And me personally, I like to add this, lavender. I like to make lavender lemonade. These right here would all be your solutes going into the solvent, water, or H20, or H2O, or just kidding, not H20. Okay, so if I have an unsaturated solution, or a homogeneous mixture, that would mean that I potentially could put more lemon, sugar, and lavender into my water, and it would still, and I wouldn't have anything settling out. I wouldn't have anything that looks like this. Okay, so I got, in this situation, this is my cup of water. Okay, I'm drawing the blue stuff is the solvent. Okay, I'm going to go ahead and add my lemon stuff. Okay, so right now, I'm going to go ahead and make these dots here to represent that this is the way that my solute mixed into my solvent. And you can see that in this kind of crude example, that there's more space left over for me to put some of my solvent into. So it's not saturated yet. It's not saturated. Okay, a saturated solution would look like, let's see. Copy that. Paste it. Alright. And let's paste it again, just so I can kind of show you a couple examples. So this right here would be the unsaturated, the first one, because I still have space that I could put in there. Okay, now if I put solvent all the way until I used up the potential holding capacity of the solvent all the way, then this right here would have 100% of the solute that it could take before it have anything settling out at the bottom. Okay, I don't have anything settling out at the bottom, right? So it's all kind of staying off the bottom of the glass. That means it's maintaining its mixture. It's suspended in mixture. So this right here would be saturated. Now, if I were to try to add more, what would end up happening is I would get my next particles to just end up on the bottom here. And that's no good because I can't really enjoy that as part of my mixture. That's wasted solute. It ends up settling out and it becomes a precipitate. So I'm going to go ahead and draw that. That's called a precipitate, like precipitation, right? Like rain. So that's precipitate at the bottom. So that's when you've gone way over the limit of what that solvent can hold. Okay, but there are ways to kind of get around that. And if you remember some of the notes we did last week, we looked at these heating curves, right? So what does this say? This is the grams of solute per 100 grams of H2O. So I'm going to go ahead and minimize this real quick so it's not all messy all over the place. Okay. And what this says is that as my temperature increases at the bottom, so as my temperature increases at the bottom, what happens to the number of grams of solute that can be held in my solution? So from 0, so I'm going to go ahead and take a look at potassium chloride here. So this is potassium chlorate. So potassium chlorate at 0 degrees Celsius, I can hold about 5 grams per 100 grams of H2O. That means in 200 grams of H2O, I'd be able to hold 10, right? I'm just doubling it, okay? So you just remember that. This is for 100. If I ask you questions about what would happen if I add 600, well, I just multiply this value by 6, right? But what do you notice for a solid? And what's your experience with a solid? If I heat up a solution, if I heat up water, it's going to mix sugar, it's going to mix lemon, it's going to mix salt a lot better than if I use cold water, right? So in general, you see that these upward trending curves, so I'm going to go ahead and highlight all the upward trending curves real quick. Oh, that's not highlighted at all. Okay, let's use blue. Okay, so all these curves right here that are going up, all these beautiful, lovely curves, that are going upward, they all have something in common, right? They all have something in common. And that if you have something that is dissolving more readily into a solution as the temperature goes up, what can be said about the state of matter of that solute? If that solute dissolves better as the temperature gets hotter, that should tell you that those blue curves are all solids. That's how solids behave. Solids, they dissolve at a greater rate the higher the temperature goes. And if you remember what I talked about last week with the soda, the lower the temperature is, the more easily that carbon dioxide is going to be able to stay in solution. The minute you release the pressure from the soda bottle, you start seeing precipitate. You start seeing that CO2 start to gas out, to bubble out. And that's because gases have a much, much lower freezing temperature. They have a much lower condensation temperature. So let's look here. I'm going to go ahead and highlight all these downward trending curves. Let's use the highlighter. It's all these downward trending curves, right? What are you noticing about the solubility of these curves? Well, as the temperature goes up, we have, see, ammonia here, ammonia, hydrogen chloride. Okay, you see that the solubility is going down. So as the temperature gets higher, I'm able to hold less grams of solute per 100 grams of H2O solvent. Okay, so this should tell you that the red stuff is a gas. Okay, because gases boil at much lower temperatures. Gases boil at much lower temperatures. So if you want to keep something in, if you want to keep a gas in solution, you need the temperature to be low, right? If you want to have a saturated solution. If you want to have a really, really nice amount of your solvent or your solute in saturated solution. Okay, so but what can I do then if I'm talking about a solid here? If I'm talking about a solid and I want to potentially get more lemonade, so right here I want to get this precipitate, right? I want to get this precipitate at the bottom of the glass to actually be suspended in the solution. I want it to mix all the way through. Well, what can I do if I want this 5 grams of potassium chlorate? If I want this potassium chlorate to actually be able to hold 10 grams, right? Well, what has to be true? I can't be at 0 degrees, I have to be at 20. So what I'm going to do is I'm going to go ahead and raise the temperature. Okay, if I raise the temperature, this guy put a fire here. Put a fire there. That's a really awful fire, but whatever. We're doing the best we can, guys. Okay, so I put that fire there, the temperature goes up, and now all of a sudden, that precipitate gets to be in solution, right? And actually, I'm going to go ahead and redraw it. So you would expect there to be a much higher concentration of dots now. In this one, you can see the spacing is much tighter because I'm able to hold more. So right here, I was able to hold more than the amount should have allowed me to. And I can do this either with raising the temperature or I can do this with pressure. And this right here is a supersaturated solution. Okay, supersaturated. Okay, now let's go ahead and actually start doing this assignment so we can get moving, right? Get moving. Okay, so let's get this stuff all out the way. Boom, 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 boom. All right, let's get rid of that. Now let's see. Well, to make this a little bit simpler, what I'm going to do is I'm going to highlight all the stuff here, or I'm going to highlight the curves as we go through the questions so that way they're not as confusing to look at. Okay, so let's look at our first question here. What is the solubility of potassium nitrate at 30 degrees Celsius? Okay, what is the solubility of potassium nitrate at 30 degrees Celsius? Okay, so let's first find potassium nitrate. Okay, potassium nitrate is KNO3. So let's see if we can find that. That's majority of it is being able to do that. And if we're doing like a challenge test, I might not tell you what the chemical formula for potassium nitrate is, right? I might just say in plain English potassium nitrate, and you'd have to use your knowledge of the periodic table and the elements to be able to tell that this is potassium nitrate, right? So I'm going to go ahead and highlight potassium nitrate with a red. Is this solid, liquid, or gas right here, guys? And we know it's got to be either a solid or a liquid, right? Because that's not the way gases behave, right? So let's use potassium nitrate right there. We'll keep that highlight mark there. Okay. And we were supposed to go to 30 degrees Celsius, so let's go to 30 degrees Celsius. Here's 30 degrees Celsius on the x-axis. Make sure you read your axes really well. Okay, potassium nitrate, so we're going to go up, 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 up. It looks like it's just under 50, so we'll call that 46, maybe to 48. If I were grading this, I'd give you the range between 46 to 48. We're going to go ahead and call that 46. Okay, so we're going to say that's 46 grams per 100 grams of H2O. Okay, H2O. Okay. Okay, next question. How many grams of ammonia, NH3, can I dissolve into 200 grams of water at 45 degrees Celsius? So let's see. So we are NH3, ammonia. Sorry, I'm still kind of getting over that really long cough I've had. We're going to highlight this green, NH3. You're more than welcome to do this too on your own. Okay, NH3 at 45 degrees Celsius. 45 is halfway between 40 and 50, so I'm going to trace up. Looks like we got about 32 grams. Okay, so I got 32 grams. But remember, this chart is out of 100, right? And this is asking me how many could dissolve into 200. So what should I do with that 32 grams? Really easy stuff. 32 times 2, 64 grams of NH3 per 200 grams H2O. And I'm going to erase some of that stuff just to show you that you need to usually put units on here because you can do some dimensional analysis stuff with it later in chemistry. All right, let's see. Group those together. Okay, what we got next? At what temperature is the solubility of sodium chloride, NaCl, the same as the solubility of potassium chloride? Okay, so we are looking for an intersection of NaCl and KCl, right? So we're looking for when the temperatures are the same. This is kind of a goofy one. So let's see, let me go ahead and highlight sodium chloride and potassium chloride. Okay, so sodium is S, right? No, wrong. Sodium is NaCl, Na, right? So that's going to be this guy here. Be very careful with your lines. NaCl, and we also had potassium chloride. Potassium's P, right? Wrong. It's KCl, right? Potassium is K. So let's use pink for that one. Okay, here it is. So we're looking for when those two lines intersect, and they roughly are going to intersect, or when do they have the same temperature? So remember, temperatures are the same grams. The grams are here. So when do they have the same number of grams? It happens to be that they intersect right here at about yellow and pink right there, right around 34, 35. Okay, around 34 or 35. Okay, let me get rid of those lines real quick. Let's see what we got here. 34 degrees Celsius is where they have the same grams that will dissolve. Okay, next, how many grams of ammonium chloride, so NH4Cl, would I need to make 300 grams of saturated solution at 70 degrees Celsius? At 70 degrees Celsius. Okay, so let's see. So NH4Cl, that's this guy right here. H4Cl. So how many would I need at 70? Okay, so 70 is right here. Go up to the blue line. That's about 61 or so. And we're doing it up to, so 61 would be a good answer, except, so here you go. You see why it's 61? So we get about 61 grams of solute would be able to dissolve at 70 degrees. But that wasn't the question. The question was, how many would go into 300? So that's 61 grams per 100. 61 grams NH4Cl per 100 grams of water. Now multiplying by what? Multiplying by 3. Right? So this will be 180. About 180. 183 grams is what I would end up getting there. Basically, it's just saying I'm multiplying it by 3 because this graph works on a 100 gram scale. And I'm going to take it up to 300. That's times 3, right? Okay. I'm going to go ahead and next questions. Okay, here we go. Let's put our graph back in here. Nope, that's not it. That's not it at all. Okay. What do all the compounds that decreased in solubility over the temperature range of the graph have in common? We talked about that at the beginning. Anything that decreased, so like this green line here, it is losing grams of solute as the temperature goes up. We said that that is not a solid, but a what? It better be a gas. Okay. What compound is least soluble at 40 degrees Celsius? Okay, 40 degrees Celsius, least soluble, so we're looking for the lowest amount of solvent, or solute that can go into the solvent, sorry. All right, and it looks like there, what do we got? Which one is the lowest one? Looks like sulfur dioxide. Sulfur and 2 oxygens, sulfur dioxide. Okay, sulfur dioxide. And finally, last but not least, what compound is the most soluble at 50 degrees? So I'm not going to go to 40 because that's where I was just at. I go to 50 and I'm looking for the lowest or the highest. I'm going to look for the highest. So we go up, 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 up. It looks like potassium nitrate. Wrong, because there is a sodium nitrate that doesn't even fit on this graph, right? So let's see. At 50 degrees, it looks like sodium nitrate would be way, 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 way up here. Way, way up here. If you're talking about stuff you can just see on the graph, on this graph right here, it looks like potassium nitrate, but actually this sodium nitrate looks like it would be much, much higher, right? And I mean, we can't see if this thing actually does like a downward curve or something, but if it did, you would see it over here, right? So I'm going to go ahead and say that it's sodium nitrate on there. You can make your arguments that it's potassium nitrate, but if you are somebody who uses deductive reasoning, right, you see the trend of this curve going up, and you assume that this is a natural substance that's going to behave pretty normally within a, 60 degree Celsius temperature range. There's some substances that behave very weird, right? As you start going into the thousands of degrees of difference, substances start turning around and doing weird stuff. They start doing really, really weird stuff, especially like superconductors, right? But this is a pretty small temperature range, and I'm going to say that this trend looks like it would continue onward up here, and so I think it would beat potassium nitrate. So sodium nitrate is the one I'm going to say there. Okay. So what would it look like on this graph if I were supersaturated? Well, at these temperatures, so let's say room temperature is about somewhere between here and here, about 20 degrees Celsius, 22 degrees Celsius, okay? So let's say I was working with potassium nitrate, okay? Let's say I was working with potassium nitrate. And at 20 degrees Celsius, I get about 33, 34, 32, I get 32 grams. For something to be unsaturated, I would be below, okay? So I'm going to go ahead and put unsaturated right there. This is below, Saturated is going to be green, and that would be right on the line. And I'm going to go ahead and make lavender above the line, super saturated. So if you were able to get more grams of solute at this temperature, it's because you did something. You might have heated it up before you mixed it quite a bit. You might have an increased pressure, and so it's able to trap more of this solvent into solution. At the ideal normal conditions, you're going to be on the curve, and that's a saturated solution. And underneath is a U. I know it looks kind of like a V. That means maybe you mixed it together when it was considerably colder, and so now it can't really mix at a rate you would want it to without having to stir or cut it up more. Okay. Well, I hope that was helpful, guys. Please send me an email, send something on the Google thread if you have any questions. But this stuff should be pretty straightforward. We'll have a Socrative practice for you ready to go. Thank you very much, and you guys did a great job last 6 weeks. Just continue to get your work done, and email me if you have any questions. Bye.